Sounds fun, right? Maybe you've heard of things called functions and relations before, but do you know what they actually mean? Let's look at their definitions to make sure. A relation is a rule that takes input values and assigns them to output values. The set of all possible input values is called the domain, which we often use the variable x for, and the set of all output values is called the range, which we often use the variable y for. We can represent relations in a few different ways, like a table, or a list of ordered pairs, or a graph. Now, a function is a special type of relation. A relation is a function if each x value is paired with exactly one y value. For example, this relation is a function because every x value is only paired with one y value. But this relation is not a function. Look at these two ordered pairs. The x value of 3 is paired with two y values, 6 and 5. That means it is not a function. Great! So for tables and lists of ordered pairs, we know how to tell if something is a function. But what about graphs, like this or this? Do we have to check every x value by hand in order to determine if this is a function? Actually, we have a convenient tool we can use called the vertical line test. To use this test, imagine drawing a vertical line and sliding it across the entire graph. On this graph, the vertical line only ever intersects our graph at a single point. It's impossible for it to intersect more than once. That means it is a function. This works because the vertical line shows us all the y values that are paired with each x value. And since a function can only have one y value paired with each x value, each vertical line should intersect our graph at most once for it to be a function. But in this graph, we see that the vertical line intersects our graph twice in most places. For example, at x equals 1, the vertical line intersects at these 2 points. That means there are two y values paired with one x value, so it is not a function. Let's try some examples. Look at this set of ordered pairs. Is the relation a function? Remember that in order to be a function, each x value can only be paired with exactly one y value. Are there any x values that are listed more than once? The x values are 1, 8, 7, 0, and -4. So each x value is only paired with one y value, which means this relation is a function. You might be worried that the ordered pairs 8, -10 and -4, -10 have the same y value, -10. But that's okay. A function can have one y value that is paired with multiple x values, just not the other way around. Let's try another. Look at this table. Is the relation a function? Once again, we need to check if any x values are paired with more than one y value. Well, it looks like there are two rows in the table where x equals 20. As you can see, the x value of 20 is paired with two different y values, 7 and 4. So is this relation a function? No, since 20 is paired with more than one y value, it is not a function. Great, let's try it out with some graphs. Here we have 4 graphs. Which of these relations are functions? Remember that we can use the vertical line test to check if a graph is a function. Let's start with the first graph. Can a vertical line ever intersect the graph at more than one point? Nope, that means it is a function. Each x value is paired with exactly one y value. How about this next graph? It looks like in most places the vertical line intersects at 2 points. For example, at x equals 4, you can see there are two y values paired with it. That means it is not a function. These next two graphs look a little bit different. The filled-in dots, or closed dots, are included in the relation, but the open circles are not part of the relation. So for example, at x equals 2, it might look like there are two y values paired with it, 2 and 7, but since at y equals 7 there is an open circle, that means it is not part of the relation. So there is actually only one y value, y equals 2, that is paired with x equals 2. So is it possible for a vertical line to intersect this graph at 2 points? No, every x value is only paired with one y value, so it's a function. All right, let's check the final graph. Does the vertical line ever intersect more than once? Yes, right here there are two closed dots, which means this x value is paired with two y values. Also, over here, the vertical line intersects the graph at 2 points. So is this relation a function? Nope. Awesome job. That was pretty fun, right? Now you are able to identify functions from graphs, tables, and lists.
Decimal grid. Before we begin, we need to understand what a decimal is and how we can represent it on a grid. A decimal represents a part of a whole. Using a decimal grid allows us to see a visual representation of a decimal. This helps us to understand how much of the whole each decimal is representing. How do we read a decimal grid? Decimal grids represent decimal numbers by showing a whole rectangle split into equal parts. These grids can be split into different numbers of parts, so it's important to look at each grid carefully. When we're figuring out what part of a decimal grid is shaded, we need to use our knowledge of place value. A grid where all of the parts are shaded represents one whole, or a 1 in the ones place. When we split this whole into 10 pieces, each section represents 1/10 of the whole, like we see here. This 10th is represented with a 1 in the 10ths place. Here's another example with the grid split into tenths. This time I see that there are 3 pieces shaded, representing 3/10ths. I'll write this in number form by putting a 3 into the tenths place. When we split our whole into 100 pieces, each section represents 1/100th of the whole. We see 1/100th shaded in this model. We can represent 1/100th on our place value chart with a 1 in the 100ths place. In this example, the grid is split into hundredths again. Now I need to figure out how many parts are shaded in all. I see that there is one whole column shaded. That means that 10 parts are shaded. There are also 5 parts in the next column, so I know that there are a total of 15 parts shaded in. Since I know I'm looking at a grid split into hundredths, there are a total of 15 hundredths shaded in. Sometimes you'll see more than one grid at a time to represent numbers that are bigger than one whole. Our steps to find the total for these bigger numbers are exactly the same. Here, I see that I have a total of 5 grids. Each of these grids are split into tenths. I also notice that 4 of these grids show that all 10 parts are shaded in, but the 5th grid is not completely shaded in. Each of these grids that are totally shaded in represent one whole. We can write these 4 wholes with a 4 in the ones place. In the last grid, I see that 1 out of 10 parts are shaded in. The last grid is representing 1/10th, so I'll add a 1 to the tenths place. In all, these grids are representing 4 and 1/10th. Let's look at another example. I see that I have 3 grids this time. 2 of the grids are completely shaded in, and the third is only partially shaded. Just like before, we'll start with the grids that are completely shaded in. I have 2 complete grids, so that equals 2 wholes. To show this, we'll put a 2 in the ones place. Now I need to know how much is shaded in the last grid. When I count the total number of parts shaded in this grid, I see that there are 30 hundredths shaded in. I notice that these 30 hundredths are also representing exactly 3 complete columns, so 30 hundredths is equivalent to 3/10ths. I'll write the value of the last grid by adding a 3 in the tenths place and a 0 in the hundredths place. In all, these decimal grids are representing 2 and 30 hundredths, which we could also read as 2 and 3/10ths because they're equivalent values. Similar problems. Remember to first figure out how many parts the grid is split into, and then figure out how many parts are shaded in.